is a PhD student from Università degli Studi di Trieste and Institut Camille Jordan, and he will tell us about singular perturbation problems for geophysical flows. So, Gabriele, I leave you the stage, and I ask to Giulia to start the recording.
Okay, thanks, Lorenzo, for the introduction. Good afternoon to everybody. Today, I will present the strategy to take the singular perturbation problem that arise from models for geophysical fluid. The main aim of the study is to analyze the mathematical model for fluid on large scale that are called geophysical fluid, like the atmosphere and the oceans. Here we have a picture of an ocean, and you can notice that the length of the ocean is much larger with respect to the height or the depth of the ocean is much larger than the height. That means that we can modelize our domain omega like R2 cross 01, R2 for the horizontal variable xh, that is for me x1 and x2, and 01 for the vertical variable x3. In the context of the geophysical fluids on a large scale, we have three main characters that drive the motion of the flow, and there are the Coriolis force, the incompressibility, and the stratification. The first main character, the Coriolis force, we modelize it like a rotation around the vertical axis. That means if we take x1, this is x1, x2, and x3, the Coriolis force is a rotation around the x3 axis. Then we can write it like E3 cross U, and this is equal to minus U2, U1, and a0, where E3 is the unit vector 0, 0, 1, the cross is the external product by vectors, and U is the velocity field, and depends on time t and position x. From the physical point of view, it is well known that the Coriolis force drives the motion to be planar. That means that the dynamics take place on horizontal plane. Here we have our horizontal plane that is orthogonal with respect to the rotational axis. And this is the so famous, so celebrated Taylor-Prodman theorem. The second main character is the incompressibility, and as we will see in the next slide, this incompressibility, this property, is linked to the pressure term gradient of P. The last main character is the stratification. That means we have the variation of the density, that in all my talk I will call it rho, depends on time and on position, and is greater or equal than 0. The presence of this stratification effect is due to the gravity, capital G. This effect acts against the Coriolis force because drive the fluid to be stratified with respect to the vertical variable. Then we have the stratification effect that drive the motion to be stratified with respect to the x3 variable. And we have the Coriolis force that instead drive the motion to be planar in horizontal plane. Okay, I think that now it's time to introduce the model, the equation, that are called barotropic Navier-Stokes equation. Actually, this is a simplified version of this model. And we have the continuity equation, okay. And the second one is called momentum equation. The first equation is an equation for the density rho and state that your density, your mass, is transported along the motion. The second equation is an equation for the velocity field u, and here you have the advective part. Here you can recognize the Coriolis term with a prefactor 1 over Rossby, and you have the gradient of the pressure with a prefactor 1 over Mach to the power 2, and the pressure depends on the density rho. And on the right hand side, you have the viscosity effect, and nu is the viscosity coefficient, and you have the Laplacian of u. As I said in the introduction, the Coriolis force and the pressure terms drive the motion of the fluid. And to translate this behavior, we take Rossby equal Mach equal a small parameter epsilon. That means that this guy is equal to 1 over epsilon. This guy here is equal to 1 over epsilon to the power 2. And when epsilon goes to 0, these two guys become singular, then tends to infinity. The Rossby number and the Mach number are a dimensional number, and the Rossby one is linked to the rotational speed, and the Mach number instead is linked to the incompressibility effect. That means if the Mach number tends to 0, the fluid tends to be incompressible. The general aim, the general goal of the asymptotic analysis to tackle this problem is to analyze the asymptotic behavior of the system. That means we would like to investigate the limit dynamics when epsilon goes to 0. This because usually the limit system is much easier with respect to the original problem, but still capture the main feature of the primitive system. This means that if you are able to describe the limit dynamics, you are also able to describe the average dynamics of the original problem. Okay, now I can start to present the main step of the analysis to tackle the singular perturbation problem. First of all, we need an existence theory. For any epsilon fixed, exists a weak solution that solves the system. This is a theory done by Lyons and Farisal. Here I recall the definition of a weak solution, that is a solution that solves the system in the distributional sense. That means that you test your equation, against the test function that belongs to C-infinity with compass support. Then for the continuity equation, roughly speaking, I can test it against phi and put the derivative on my test function. In a similar way, I can rewrite the momentum equation in the following way. At this point, we have found that for any epsilon fixed, exists a weak solution rho epsilon u epsilon. This is a u epsilon. Okay, now we would like to find uniform bounds for these families of solution in order to extract weak limit points. What does it mean? If, for example, you have uniform bounds for the density rho epsilon in a suitable space that is less than a constant, this implies that you can extract a weak limit point rho. And these uniform bounds come from the energy inequality, that is the following one, and where the kinetic energy, the entropy energy, and also the viscosity effect are bounded from above by the initial datum and the initial energy function. Then now we have to find uniform bounds for this initial datum, for the right-hand side of our inequality. We take initial datum that are small perturbation of a constant profile. For simplicity, I take the constant profile equal to 1. And you can show that the entropy functional behaves like rho 0 epsilon minus 1 to the power 2. This means that this behaves like epsilon to the power 2 R0 epsilon to the power 2. Then if you look at these guys here, this epsilon gives this one. For rho 0 epsilon, you know that you have uniform bounds. Then this guys here is bounded from above by a constant. This guys is bounded by a constant for free because you have initial data that are uniformly bounded. Then all the right-hand side is uniformly bounded. And then also your left-hand side is uniformly bounded. And from the first term, you recover the uniform bound for the velocity field. For the second one, you recover your uniform bound for the density. And here you can recover the uniform bounds for the gradient of the velocity. Okay. As I presented before, we have singular terms in the equation that when epsilon goes to 0 tends to infinity, then are singular. For this reason, we have to require that at the limit, the pressure term and the Coriolis force vanish, then are equal to 0 when epsilon goes to 0. If you look at the pressure terms and you do a Taylor expansion at the first order, you can rewrite it like 1 over epsilon p prime calculated in 1 gradient of r epsilon. This because you have to remember that your rho epsilon is 1 plus epsilon r epsilon. Okay, for simplicity, we take this one p prime in 1 equal to 1. And then you can notice that the pressure terms and the Coriolis force scale at the same level. What it does mean? It means that we have a prefactor that is equal and it is equal to 1 over epsilon. Then you can pass to the limit for epsilon going to 0. And you find in d prime that the gradient of r plus E3 cross u is equal to 0. This because these guys here, these guys here converge to capital U because rho epsilon converges to 1, and these guys here converge to gradient of r. Now I rewrite this relation by components in an explicit way, and this relation is called quasi Geostrophic balance. And from that relation, I have two properties. The first one, the horizontal divergence of the velocity field, that by definition is d1 u1 plus d2 u2, is equal to 0. This because if you take d1 here, then you have d1, d2 here, d2 here. You can notice that you have the same quantities, but with opposite sign, then are equal to 0. If you look at the last row, you have d3 of r equal to 0. That means that d3 u2 and d3 u1 is equal to 0. This means that your horizontal component of the velocity field, that for me, this means u1, u2, depends only on the horizontal variable. Again, this is equal to x1, x2. Because the derivative with respect to the vertical component is equal to 0. What about u3, the third component of the velocity field? From the continuity equation, and you subtract the constant profile equal to 1. Again, you remember that rho epsilon is 1 plus epsilon r epsilon. Then rho epsilon minus 1 is of order epsilon, and also for the initial data. For epsilon going to 0, this goes to 0, and this goes to 0. And this one converts to u. Then at the limit, you have that divergence of u is equal to 0 in d prime. Okay, d prime, sorry, maybe I have to specify, is the distributional space. From the previous slide, we have seen that the horizontal divergence of UH is equal to 0. The adding these two information, we have that d3 u3 is equal to 0. Then u3 depends only on the horizontal variables. And thanks to suitable boundary condition, you can also prove that u3 is always equal to 0. At the end of the day, you have proven the so-called Taylor-Pradman theorem that states that your velocity field is 0 on the third component, and the horizontal component of the velocity field depends only on the horizontal variable. Okay, as a last step of our analysis, we would like to describe the limit dynamics of our fluid. Then we would like to pass to the limit in the momentum equation, testing this equation against test function of the following form. This specific form is due to the constraint at the limit. I would like only to say that in the momentum equation, in this equation, the worst term to deal with is the convective term. And in general, this because you have that if f epsilon converges weakly to f and g epsilon converges weakly to g, this does not imply that f epsilon, g epsilon converge weakly to fg. Then, very roughly speaking, you need some strong property to pass to the limit in this term here. Let's analyze this term. You take v epsilon equal to rho epsilon u epsilon. Then you have to believe me, you can rewrite your original problem in the following way, that is called wave system, that in a compact form reads as follows. This is epsilon dt r epsilon v epsilon plus an operator a applied to r epsilon v epsilon equal epsilon something. And here I put also the definition of a. But what is important to notice is that in front of the partial derivative in time, you have the epsilon. That means that you have fast oscillation in time for the solution, and this may prevent the convergence at the limit. To overcome the issue, you split your solution R epsilon v epsilon into parts. The first one, k applied to R epsilon v epsilon plus q R epsilon v epsilon, where k is the L2 orthogonal projection into the kernel of your operator. Then, if you apply k here, and k here, and k here, you notice that k is in the kernel, then this guy is equal to 0. Now you have epsilon dt k R epsilon v epsilon equal epsilon something, then you can kill also the epsilon. You know that this force on the right-hand side is uniformly bounded in suitable spaces. Then at the end of the day, you can say that dt k R epsilon v epsilon is uniformly bounded in suitable spaces. Then thanks to an Ascoli-Arzelà argument, you can converge to the limit RU. For the other part, you use dispersive estimate to state that the Q converges to 0. Another approach, a different approach, is to use the algebraic structure of the wave system that I presented before to find special cancellation that allow you to find strong properties in order to pass to the limit. The last issue is due to the Coriolis term, that is a singular term present in the equation here. But this is a standard matter. You use the form, the special form of your of your test function, and then you can rewrite your Coriolis term like 1 over epsilon double integral rho epsilon u epsilon h c dot gradient of v. And this is, if you integrate again by parts, is minus double integral 1 over epsilon divergence h rho epsilon u epsilon h, sorry, phi. And you can notice that this term here is the same term that appears in the continuity equation. Indeed, if you remember, the continuity equation is dt rho epsilon plus divergence rho epsilon u epsilon equal to 0. Indeed, you take advantage of the continuity equation in the following way. You subtract the constant profile, you divide it by epsilon, then you have to multiply by epsilon. And then here you have, you can recover the term that you need. And then you can rewrite your Coriolis term in terms of R epsilon and R0 epsilon, the initial data. For these quantities, you already know the convergence and the limit, then you have done. This concludes the strategy to tackle this kind of problems. To resume, now I resume the main step of the analysis. So the first step is to have an existence theory. Second step is to state uniform bounds for your weak solution. Then you can extract limit point. 3, you have to assume condition, then you have to impose constraint at the limit. 4, you have to deal with the convergence. Okay. Now I would like to present another problem that is a more complicated problem, but also is much physical relevant. And this is the full Navier-Stokes Fourier problem. And in this work, we deal with the variation of density, but also the variation of temperature. We take into account the presence of the gravitational force and the centrifugal effect. We deal with also the stratification. And in the end, this is a multi-scale problem. That means we add in the equation a parameter that allows us to consider all the possible regimes of the fluid dynamics. Okay, here you can see the equation. You immediately recognize the continuity equation. Here you have the momentum equation. And in addition, you have another equation that is called entropy balance. And now I will comment a bit this equation. In the momentum equation, we have a more complicated term, that is the divergence of the viscous stress tensor S in place of the Laplacian. Before we have the new Laplacian of u epsilon. In addition, we have two external forces, the centrifugal force, gradient of F, and the gravitational force, gradient of G. Also, it is important to notice that our pressure terms depend also on the variation of temperature. Here, theta for me is the temperature. And as I said in the previous slide, we introduce this parameter m that allow us to deal with all the possible regimes of the fluid, because M, it is free to vary for all the values greater or equal than 1. Okay, then from the continued equation, we have an equation for the density. For the momentum equation, we have an equation for the velocity field. What is missed an equation for the temperature. And we can recover this equation for the temperature from the last equation. You are right, this is an equation for S, this is the specific entropy. But since you already have an equation for the density, you can read this last equation like an equation for the temperature. Okay. In this problem, we have two main scenarios, the anisotropic scaling and the isotropic scaling. In the anisotropic scaling, when m is greater or equal than 2, or m strictly greater than 1 and def equal to 0, some effects are predominant in the dynamics with respect to the others. Instead, in the isotropic scaling, when m is equal to 1 and def equal to 0, all the effects act at the same level. Then we have two main scenarios. For this reason, we have two main theorems that describe two different limit dynamics. Let's take the theorems. The first one for the anisotropic scaling, m greater or equal than 2, or m strictly greater than 1 and f equal to 0. We take initial data that are a small perturbation of constant profile and uniformly bounded. Then at the limit, we can find that the density is constant. We are able to measure the deviation of the density with respect to the constant profile with this rate of convergence. And also we can describe the limit profile of the velocity field that satisfy the Taylor-Pradman theorem and the incompressibility condition. That means that the divergence of the velocity field is equal to 0. Moreover, the triplet UH, capital R, and capital theta solve in the distributional sense the Obebach-Busnest system. That is the following one. We have the Busnest balance, that is a balance between the gradient of the target density and target temperature with external forces. We have a Navier-Stokes type equation for the velocity field. And I stress that the dynamics is purely horizontal. And for the target density, for the target temperature, capital theta, you have a transport diffusion equation. Here you have the transported part, and here you have the diffusivity part. And in this last equation, we are able to capture some low stratification effect because capital theta depends on T, XH, but also on X3. Now, for the isotropic scaling, when m is equal to 1, we have the same convergences as before with a different rate. We have the Taylor-Pradman theorem and the divergence precondition. But now the right unknowns to look at the limit are the following one, upsilon and q, where upsilon is a combination of target density and target temperature, and q takes into account also the gravitational effect. In our problem, the gravitational effect are equal to minus x3. Then a priori, q depends on t, xh, and x3. But surprising, you can find that q depends only on the horizontal variable. And also, it is a stream function for the velocity field. This is the quasi-geostrophic balance that we have seen before. Moreover, the couple q upsilon satisfy a quasi-geostrophic, higher order quasi-geostrophic type equation for q. And also in this case, the dynamics is purely horizontal. and again a transport diffusion equation for upsilon. Okay, I will conclude my presentation, and I think that I'm time, presenting some open problems. This is the case when M is between 1 and 2, and we consider also the centrifugal effect, then F is not equal to 0. And the case when M is equal to 1 and F not equal to 0. Here, there is my last slide, where you can find the main references to my talk. I would only to say that the first problem is a simplification of a model that you can find in this paper by Faraisel, Garagher, and Novotny. And the second one, the full Navier-Stokes Fourier problem, is the subject of a paper that we did with my supervisors and a Polish collaborator, and is present in this article. Okay, I think I can stop here. Thank you very much for your attention.
Thank you, Gabriele.